With this having said, so thanks for the introduction. I can skip this first slide. I want to quickly introduce the International Audio Labs to you. That's where I'm working. So the International Audio Laboratories Erlangen are a joint institute of a Fraunhofer Institute, IIS, and the university here. And to understand the construction of the audio labs, you need to know that Erlangen is the birthplace of MP3. So Erlangen has seen major developments, and Fraunhofer took care of standardization, making it run. And finally, it became a success. And from the license money, Fraunhofer gave back part of the money to the university to, for example, found the audio labs, which consists of 6 professorships. Currently, we are only 4, and we all work on audio. So there are some professors coming from the, let's say, MP3 family, the original one, working on audio coding, psychoacoustics. There are professors for virtual acoustics, spatial audio, multi-channel audio. Of course, we also now do deep learning, machine learning. And last but not least, I was happy to get the professorship for semantic audio processing, where this means for me, so semantic means in my context, in particular, music processing. Uh, the thing I'm most proud of is my research group. So here you see on the left side my current research group, and on the right side some former members. And I really want to thank them because without them, I could not do the kind of research I'm doing. In particular, I want to introduce to you 3 PhD or former PhD students. So first of all, Simon Schwer is working on intonation analysis, or more general analysis and synthesis of singing voices. So in this context, we also study the behavior of general loss functions, for example, optimal transport or multiscale spectral losses. This will play a role later in the presentation. Then Johannes Zeidler is a current PhD student who's mainly working on soft alignment techniques or differentiable alignment techniques. And last but not least, I want to mention Michael Krause, who finished his PhD in 2023, so 2 years ago, and he worked on sound activity detection, for example, singing voice or instrument activity detection, or as another topic, finding leitmotifs in Wagner operas. This having said, I want to emphasize that all their work can be seen within the context of differentiable signal processing and model-based deep learning. So that are topics we also discussed in our recent overview article initiated by Gail last year. And as we argued in our paper, we said that in model-based deep learning in general, one may think of various sources of knowledge. So can be, for example, signal processing knowledge using signal models or physical models, instrument models, musical models, certain theories, for example, on harmony analysis or structure analysis, and last but not least, perceptual models. And all these sources of knowledge can influence, inform, or can be integrated at various stages of the machine learning, audio, or deep learning processing pipeline. And in this talk, I want to focus at the last stage, at the loss function stage. In particular, I want to, so to say, as case studies or examples, cover 3 different topics. First of all, I want to revisit multi-scale spectral loss, where the knowledge source in some way is a signal representation model, spectrograms. Then I want to discuss a hierarchical classification loss, where the knowledge source is a musical hierarchy, so it's musical knowledge. And as a third case study, I want to touch on differentiable alignment losses, where the knowledge source is, so to say, information on temporal coherence. So let me start with the first topic. This is work which was mainly inspired by Turian and Henry in their paper, I'm Sorry for Your Loss. And Simon then had a closer look at the multiscale spectral loss. And this is what I try to summarize in the next 20 minutes or so. By the way, if there are questions in the audience, also feel free to interrupt me. And then we can also have short question answering sessions in between. Okay, so to better understand the multiscale spectral loss, let's do some sort of a thought experiment. So let us start with a simple signal, a sinusoidal of a fixed target frequency, let's say 1000 Hertz. So something like this. That was also a sound check. Okay, so that's our target. That's a waveform, so to say, which is parameterized by frequency with a target frequency of 1000 Hertz. And let's say we have a second signal that comes from the same family of signals with an estimated frequency of 750 Hertz. So sounds like this. And let's assume we have a fixed loss function, a black box loss function that allows me to compare these two signals in some way. Now, in this case, the estimated signal and the target signal, they are not close by. So the loss, assuming that's normalized between 0 and 1, may be something like, let's say, 0.5. So not very close. Now, when I shift the estimated signal towards the target signal, for example, now having an estimated frequency of 972 Hertz, then the loss should be much lower. Yeah. Finally, at the estimated signal of 1000 Hertz, the loss should be 0. And then going beyond that target frequency, again, the loss increases. So in this simple example, we have, so to say, a signal space parameterized by a single parameter, the frequency. That's a one-dimensional, so to say, a one-dimensional space of estimated signals. And that allows us to plot the loss landscape or the loss function over the entire parameter space, yielding what we call a loss function, what we call a loss landscape. So the loss landscape is over estimates for a given fixed target. And yeah, you can see that the loss landscape has a dip towards the target frequencies, and otherwise it's pretty high. Okay, so let's look at different loss landscapes depending on the loss function. So this brown loss function here, we will discuss later. Now, when I have a loss function that would directly compare the parameters, that's a trivial loss function. Yeah, it exploits explicitly the parameters, and you would just take the difference of the parameters. You get an ideal convex loss. Now, that's not what we do in, for example, DDSP, right? In these cases, we compare the signals, so to say, on the waveform level or on the spectrogram level. So let's look how the loss landscape looks like when using the standard multiscale spectral loss. At this point, I would love to be in the room because you should be shocked. You should be shocked about this loss landscape. That's the real loss landscape you get from MSS from this very simple, within this very simple scenario. It's completely messed up. It's not at all convex. It has many local minima. It has ripples. It is completely noisy. So this is the loss function we widely use in audio processing, in DDSP, without further thinking of what we use. So let us go into more detail what and why this happens. So let's go through this definition. The definition of a spectrum and the definition of the multiscale loss, MSS loss. So that's really standard. So first of all, we have an input signal, that's X. Then in the STFT, we have the parameters window size and hop size. So in the following, we assume that the window is something like 64, 512, 2048. The hop size is usually half of the window size, let's say. Then we have a window type, typically Han window. One may also take other windows, rectangular window or flat top window. Let's see. Then one often applies logarithmic compression, converting magnitudes to decibel, for example, but there are also other choices of magnitude compression. Then to compute the loss, we need a distance function. Could be, for example, the L1 or the L2 distance between spectrograms. Then in the multi-scale case, we not only consider a single window, but we consider families of windows. For example, several windows, 64, 128, 256, and so on. So multiple scales and add up the corresponding distances. And last but not least, one can also look at multiple compression functions, for example, no compression at all and decibel scale, and add the corresponding distance, add them up. So in the standard multi-scale spectral loss setting, one has the following configuration. Han window, WH. Window sizes is, as indicated, 64 to 2048, different sizes. Then as for the magnitude compression, it's a combination of using no compression and using decibel, basically, or log X plus some epsilon. And last but not least, they use an L1 distance. So this is the standard setting in MSS. With this in mind, let's go back to our EC thought experiment, where we have a single target frequency f of 1000 Hertz. And let's use a Han window. For the moment, the size does not matter so much. Let's take the Han window and let's compute a single frame, of the spectrogram, which is plotted on the right side. So a frequency-dependent representation. Please note that on the left side here, the amplitudes are shown here in a decibel scale. Yeah, so some artifacts are overemphasized in this representation. Okay. And then what you can see is because of the spectral leakage due to the windowing, one has main lobes around the target frequency or the main frequency, and one also has side lobes, so ripple artifacts. Okay. And then we are dealing with discrete STFT. So I show a continuous frequency Fourier representation on the right side, but in the discrete case, we sample certain frequencies. So we compare the spectrograms by means of the big black points on a frequency grid. So this is what we use for comparing different spectra. Okay, now let's slightly increase the frequency f, which is next shown in red. So I just increase from 1000 Hertz to 1003.9 Hertz. And then in red, you see the corresponding spectrogram. So you can already see that while for the first signal, the frequency grid directly matched to zeros in the side slope areas. Now slightly shifting the frequency, the frequency grid matches the side slope maxima of the second signal. So when I would compare the two spectra, then the distance I get is pretty large because of the side slope artifacts. So the distance between the spectra depend very much on the grid sampling or the properties of the main lobe and side lobes. And that in turn depends on the window type and the STFT parameters. So that is classical signal processing. Now let's move on by again slightly shifting the estimated frequency, the red one. And here you can see that I'm again lucky in some way, because now again the frequency grid again touches the zeros of the side slopes. So in this case, the loss is even smaller, even though the distance of the two frequencies, 1000 and 1007.8 Hertz, is larger than before. When I further increase again the frequency, again the distance, the loss may become again very large. So in other words, this thought experiment shows that when I shift the estimated frequencies over the frequency axis, I get ripples in the loss function. They're becoming larger and smaller, larger and smaller, and the ripple properties depending on the SDFT parameters and the window type. Okay, so let's look at different window types. That's the Han window typically used in MSS, standard setting, and the corresponding Fourier representation. Okay. As for the rectangular window, the proportion between the height of the main lobe and the side lobe is even worse. Yeah. So one would expect that artifacts become larger. And then as a third example, one may take a flat top window where even in the logarithmic magnitude domain, the ripples are hardly visible. But so to say, as another property, the main lobe width becomes much larger. Let's have a look on how the window type influences the loss. That's just so to say to indicate how this looks like when I look at an estimated signal of 1020 Hertz. Okay. Let's look at the effect on the loss landscapes. So as I said, I exaggerated the effect of ripples a bit by using a decibel scale beforehand. Now the comparison is not done in the compressed domain here. So in the Han window, you see the loss landscape, and you see that there is a dip in the neighborhood of the target frequency. So when the estimate hits the target, the loss is 0, and when the estimate is far outside the target frequency, the loss is basically constant. It's 1. So vanishing gradient is another point, but I don't want to touch on this in the moment. So let's just look at the artifacts for the moment. Now switching from Han to rectangular window, you can already see all the small ripples that come from the grid frequency falling on zeros or local maxima in the side lobes. As for the flat top window, the dip in the loss functions becomes much wider because of the larger main lobe, but the ripple artifacts are hardly visible. So that was the observation 1. Let's move on to observation 2 by investigating the window size. So fixing the Han window, you see here 3 different window sizes. A standard one, let's say 2048. Then making the window size smaller, yeah, the spectrum is smeared. So the main lobe becomes larger, also the width of the side lobes and so on. So everything is stretched out, and making the window size larger, you have a better focus in frequency. And when you look at the corresponding loss functions, the effect should be pretty clear. When you make the window smaller, the loss dip, so to say, becomes wider because the main lobe becomes larger and they have more overlaps between target and estimate in the frequency domain. And the window is very large. The loss dip becomes very narrow because the main lobes hardly overlap. Okay. Next observation. What's happening when we apply logarithmic compression? So in this plot, you see in the first row the spectra when not using any compression. again using a Hahn window. So as I said, the ripples only become visible when you convert to the decibels to the decibel scale when you apply logarithmic compression. That's the second row. So here the side lobes really become a major issue. And then rather than just taking the log, you can also take log of 1 plus value. So that stabilizes the logarithmic compression. It's a compromise between the two first cases, so to say. The effect on the loss landscape may be dramatic. So if you don't use any compression, you get the first row loss landscape. If you just convert to decibel scales with a machine epsilon to avoid numerical instability, you get all the ripples reflected in the loss landscape. And then, as I said, the third part is some sort of a compromise. You get some ripples, but it's not completely destroyed the structure. Now, with this in mind, let's go back to the original setting of MSS, where we use a Hahn window. So one may think, not too bad. But when you use then also a compressed version in as one term in the MSS loss, the side slope thing becomes dramatic. So it is so noisy because the result of the spectral leakage, so to say, impacts the loss landscape at different window sizes. The ripples are amplified by logarithmic compression. And another important point, when you use window sizes that are multiples of each other, so powers of 2, 64, 128, 256, and so on, then the grid structure, they are coherent across the window sizes, meaning the frequency grid may always, for all windows, correspond to zeros in the side slopes, or they all may correspond to the local maxima in the side slopes. So this grid consistency over these window sizes may amplify all the artifacts. And that's the result why the standard MSS loss looks so poor. Let's look at another example. So basically just changing the window sizes from 64, 128, and so on to some window sizes that are not related by powers of 2. So just taking 67, 127, 500, 257, 509, and so on. Disregarding efficiency issues for the moment. Yeah. So maybe you cannot directly apply the FFT, but disregarding this, you can already see that the resulting loss landscape is already much closer to what you would expect. So the ripple artifacts, they don't add up constructively as in the standard setting, but they may even cancel out destructively when not having this regular structures. And replacing the Hahn window, for example, by a flat top window, and replacing the decibel scale by the softer log 1 plus gamma x version of compression, you may get in this thought experiment a very smooth and soft loss function. And this is the loss function I showed at the very beginning. So this has been, of course, just anecdotal evidence that the loss function may be quite noisy due to poor parameter settings. To quantitative evaluate this, we followed the original approach by the authors. Sorry for your loss. So we used a measure called gradient sign ranking accuracy. So the intuitive definition is that this measure basically indicates how often the loss gradient points in the correct direction. Yeah, we have a one-dimensional parameter space. It can show to the left or right. And choosing a target and estimate, so to say randomly, you can then, so to say, see if the gradient points numerically to the left or right towards the target or away from the target. And then there's a step size parameter that tells you, so to say, the distance you use to numerically approximate your gradient. So that's a sort of, It indicates, so when the step size is small, for example, 3 cents or 30 cents, it describes more the local properties of the loss landscape. And if the step size is large, like 300 cents, it describes more global trends. And you can see when the step size is very small, so 0.3 cents, then in standard MSS, you get 0.52. That basically means it's random guessing if you go to the wrong or right direction. Whereas for the smooth MSS, you always go to the right direction on a micro scale. And also on larger scales, so to say, the smooth MSS has much better properties in terms of this GRE measure. So I don't want to suggest that you should use the setting we used in smooth MSS. As I said, this was just anecdotal evidence what may go wrong. We just wanted to indicate that the loss function may matter and the parameters are essential. We did some experiments with DTSP, using the work from Engel et al. And one reason why they use so strong priors, for example, when they synthesize signals, they assume they basically have the F0 estimate and so on. And one reason why they use so strong priors is that the loss landscape is really poor. Okay. So with this, I would finish the first part and I would go into the next topic, hierarchical classification loss. Okay. So then I will go to the second scenario where I want to talk about a hierarchical classification loss exploiting musical hierarchies explicitly. This was part of Michael's PhD thesis. Okay. So to give you some more context, let me start with the musical setting we have studied over the last 10 years in my group in different scenarios. And one outcome was that we published a data set called Wagner Ring dataset. So Der Ring des Nibelungen is a cycle of 4 operas. It's a tetralogy where altogether these 4 operas consist of 11 acts. It's roughly 16 hours of music. So each opera is 4 hours. 4 times 4 makes 16. And altogether there are roughly 22,000 measures. So for example, you may know this piece, part of Die Walküre, the Valkyrie, how to say, Walkürenritt. I don't know how to say it in English. Okay, so it's highly complex orchestral music. There's also singing and so on. And we have several levels of annotations there. So first of all, we try to also generate a symbolic representation by starting with a symbolic piano-reduced score. Already the piano-reduced score is nearly 1,000 pages. It's more than 800 pages. And we used optical music recognition and manually corrected this. That was a 2 years project with student assistants. So, and then we also collected audio recordings. So we have 16 performances of this 16 hours of operas, altogether roughly 200 hours of audio. And among the 16 performances, 3 are in the public domain because they are old recordings. And we have made this available to the community along with various annotations. First of all, we provide measure annotations for all audio recordings. Some of them generated manually for 3 operas, and the others then transferred automatically using music synchronization techniques. Then we also provide note event annotations, singing region annotations, time and key signature annotations, and so on and so forth. So when you really want your beat tracker or downbeat tracker to see failing, then please use the Wagner ring data set. So nothing will work as you think it should work. Okay, so this was, so to say, the musical setting. And Michael used this data set for activity detection in general. So given an audio recording,
Komm, mein Schwert, schneide das Eisen.
he wanted to solve tasks like where are singers active and where do certain motifs occur or where are certain instruments active. So that was the general setting. And within these scenarios, I will concentrate now on singing voice detection to then discuss the loss function. Okay, so singing activity detection is just the binary problem that for each time point, you want to determine if one of the singers is active or not. And you can, of course, consider a more fine-grained problem, for example, also finding out in case there is singing activity, is this a male singer or a female singer? So that's a gender classification problem. Or even more fine-grained, you also want to find out the voice type. So for example, within the male category, is it a bass?
Mit starker Waffe doch wehre dich Norge.
Is it a baritone or a tenor?
Komm, mein Schwert, schneide das Eisen.
On the female side, you may want to distinguish between alto, mezzo, and, for example, soprano. So there's a natural hierarchy of these classification problems. And in the following, I want to discuss various strategies to solve this multi-class hierarchical classification problem. The strategy is called A, B, C, D, and D alpha beta. I will skip C because that's very close to B. So let's start with strategy A. So in strategy A, I simply train and evaluate separate models for each hierarchical level. So I consider these three completely unrelated classification problems. For each hierarchy, I even have an independent model. So I have an activity classifier, a gender classifier, and a voice type classifier. And of course, the problem is when I do it in this way that the outputs may be inconsistent. So the gender classifier may say it's a male, but the voice type classifier may say it's an alto. So it's inconsistent. It's musically not meaningful, this result. To make it consistent, a simple strategy is bottom-up aggregation. So you just train a classifier on the finest level, on the voice type classifier. And once it's classified, you just propagate and aggregate results from lower levels to upper levels. So once something is classified as bass, baritone, and tenor, you also say, okay, it's male, and vice versa for the female. In this case, consistency across hierarchical levels is trivial. Yeah. However, when you have poor predictions on the fine-grained level, these errors are propagated onto higher levels. Yeah, so that's you cannot recover from prediction errors. So that's a disadvantage. Okay, so let's look at strategy D, where rather than having separate models for all hierarchical levels, we have a single model which solves all three classification problems at the same time. So this becomes a multitask model. Yeah. So you have several classes for each hierarchical level, one class that should be active, so to say. However, if you don't have any additional loss function, again, this may promote inconsistent predictions. So I now introduce a loss function that promotes consistency. And that becomes the strategy D alpha beta being hyperparameters. Okay, so let me start with some light notation, but I will try to explain it in an intuitive fashion. So let's assume we have a class called C, And with C, I also have a probability called PC. And for a given class, if it's not on the lowest level, it may have child classes, here denoted by C arrow down. Typically, I will denote child classes by C prime. So I have a parent class C and child classes C prime. So the parent may be female, the childs are alto, mezzo, soprano. Okay. Now let's first look at bottom-up consistency. So intuitively, if a frame is classified as a child, for example, let's say it's alto, then to have bottom-up consistency, the frame, the parent, so the frame that should be also classified, so to say, as its parent C. So when a frame is classified as alto on the lowest level, it should be classified female on the upper level. So when I reframe this bottom-up consistency in a soft way, then one could say that if PC prime, for example, C prime being the alto, is high, then also PC, where C is female, should be also high. So when the probability is high that the frame is classified as alto, then also the probability of the frame being classified as female should also be high. Or just putting this in other words, PC should be at least as high as any PC prime, C prime being a child of C. So we can introduce a penalty whenever PC prime becomes larger than PC. And this is basically expressed by the loss term I've indicated here. So when PC prime is larger, then the max is also larger than 0 and the loss is high. And when PC prime is smaller than PC, then the max is 0 and loss is also 0. So that's a bottom-up loss term. And now we can do the same. I make this a bit shorter for the top-down case. So top-down means if a frame is classified as parent, for example, female, then there should be one child, C prime, for example, alto of C, such that the frame is also classified as this child, alto. So in other words, on the soft side, if PC, for example, female, should be above the largest PC prime. Yeah. So the probability for C should be larger than the largest PC prime to have top-down consistency. And again, you can rephrase this in terms of a loss term. And now you can add up all these small loss terms across all classes and all hierarchical levels. And that gives you a bottom-up loss term, a top-down loss term, and finally, you can combine the cross-entropy loss for classification with bottom-up and a top-down loss term weighted by hyperparameters alpha and beta. So this loss design is really coming from musical knowledge, from this hierarchy to start with. Let's look at some effects. So when I would train with strategy A, where all the classifiers on the hierarchical levels are independent, then you may typically get a pretty good result in terms of frame-wise F measure. Yeah, so in this case, it's maybe 92%. However, when you look at consistency, bottom-up and top-down consistency jointly, I don't go into detail how this is computed, but it expresses how consistent the classification is. It may be pretty low, just in the 70s, for example. When I use strategy B, then the consistency is perfect. It's 1.0, 100%, so to say. However, on the frame-wise accuracy level, the strategy performs much poorer than before because of this error propagation. And now doing, so to say, a joint training of achieving a good accuracy and high consistency, you see here a typical result. where you get an accuracy that is nearly as high as in strategy A. So, however, the consistency is much higher than in the A case. Yeah. So, by having these soft loss terms that enforce consistency, you become not necessarily a better accuracy, but your classification results become much more musically meaningful. So that was a second example. And of course, you can then apply it to other hierarchies. So Michael also used it for instrument activity detection, where you also have natural hierarchies, considering, for example, instrument families like woodwind, brass, and so on. And then on the finest level, the individual instrument types. Okay, so then the third example I wanted to give to you is differential alignment loss function, in particular uh, uh, um, um, soft dynamic time warping. And this is work by Johannes, I do with Johannes Zeidler. So just to quickly recall what alignment is about, let's look at classical audio-audio alignment, where you have, for example, two audio recordings, could be also an audio recording and a symbolic representation, yeah, but you have two representations of the same piece of music. You would convert this into a joint feature representation, for example, chroma features, so 12-dimensional feature vectors over time, each feature vector expressing the pitch class distribution locally of the audio signal. So I assume that you are familiar with that for the moment. And then you would compare the two feature representations to compute a cost matrix. And then in classical dynamic time warping, you would then try to find a cost minimizing warping path or alignment path. So that's a data structure that assigns time frames of the two sequences with each other. And there are certain constraints with the warping path. There's a boundary condition. So you assume that the beginnings and the end positions are aligned, assuming global correspondence. Then there is a step size condition, meaning you can only move horizontally, vertically, or diagonally one step at a time. And monotonicity means you cannot go back in one sequence and move on with the other one. Okay. So that is then rephrased and then rephrased as an optimization problem. And the warping path then corresponds what is typically referred to as strong alignment. So the strong alignment, as I said, is giving you a pairwise alignment of time frames in this case. So each time frame in one sequence is aligned to a musically, semantically corresponding time frame in the other sequence. So this was a short reminder, and now it becomes quite technical. But I try to do it in a way that things become somehow intuitive. So in the feature learning context, you may have similar problems. So let's say you have an audio recording on the one hand side, and rather than having a second audio recording, as in the audio-audio synchronization case above, let's say the second sequence is coming from a symbolic score. It's a target sequence. Yeah, it indicates the notes occurring in the piece, also encoded by some sort of a piano roll or MIDI representation. And then the goal of the neural network would be to, given the targets and the audio recording, find a feature representation that is somehow close to the target. Let's say that is our problem. And once you have a strong alignment between the outputs and the targets, you can just use binary cross entropy, so to say, as a frame-wise loss function. So for that, you would need strong aligned targets. So each frame of the output needs to be assigned to a frame in the target. And often this is hard to obtain. A weaker condition on the targets is if you only know that the target and the output, they globally correspond, but you don't know locally how the assignment is. And this leads to a notion which is typically called weak alignment. Yeah. And then the idea of end-to-end deep learning is that the alignment becomes part of the loss function, only requiring weak alignments, but still the loss function needs to be differentiable. And you cannot simply use dynamic time warping as a loss function because it's non-differentiable. And that's the reason why people have started using soft approximations of dynamic time warping. And this is what I'm talking about in the next 5 to 10 minutes. Okay, let's do some mathematics. You are engineers, so I think you like some formulas. So let's assume you have two sequences, x and y, of length n and m. So x and y are our chroma features or encodings of our targets. And the features live in some abstract space, a feature space. And so this is an alignment as indicated before. And you can encode an alignment also in form of a binary matrix. Yeah, so think of a structure that has the same format as the cost matrix, and all the aligned cells, so to say, they are encoded by pairs. They can be encoded by a 1 in this matrix, and all other cells are 0. So this is just a re-encoding of an alignment of a warping path. And I call this now alignment matrix. So a binary n times m matrix. And of course, this one structure, it has to fulfill the same conditions as the warping path. So boundary, monotonicity, and step size condition. And I want to denote the set of all possible alignment matrices, fulfilling these conditions as calligraphic A and M. So that's a subset of all possible binary matrices. So that's the set of all possible warping paths. That's a huge set. It explodes. The size is exponential in n and m. This number is also known as Delaunay number. Okay. So let's rephrase dynamic time warping as an optimization problem. So I assume that I have a local cost measure that allows me to compare the two elements of the feature space. From that, I can compute a cost matrix. It's an n times m matrix. So it has the same dimension as the alignment matrix. And then the cost of the alignment can be just expressed by the inner product of the binary alignment matrix and the real valued cost matrix. And then the dynamic time warping cost can be phrased as taking the minimum over all possible alignments of the inner product of A and C. That's still classical dynamic time warping. And then the optimal alignment path is just the argmin of this optimization problem. Okay, so that's again just the dynamic time warping cost. And then probably you know from your lecture, if Geoffroy is using my textbook, you definitely also study dynamic time warping. Geoffroy, I hope you did that. You know that you can compute the dynamic time warping cost and an optimal alignment efficiently using a recursion called also Bellman's recursion, which is here expressed by the D matrix, which needs to be initialized. And then for a given cell Nm, it's just the minimum of 3 predecessors that come from the step size condition. Yeah, one cell to the left, one cell to the from the bottom, and one diagonal cell. And then this can be computed efficiently in n times m, complexity-wise. As I said, neither the cost function nor the recursion is differentiable with regard to the cost matrix because of the min operations. So the idea is to replace the min function by a smooth version. For example, by the smooth min function. This is just the definition of given a set of real numbers, then the smooth min is, or the soft min, I should say, the soft min is defined as summing over exponentials of the values and then taking the log of the sum. And the gamma is called hyperparameter. So if gamma approaches 0, you get the original min. And if gamma becomes larger, the min function, the soft min function becomes softer and softer. Okay. And we can use exactly this soft min in the definition, in the global definition of the global dynamic time warping cost, called now SDTW, depending on the hyperparameter gamma. And the only thing we do is we replace the minimum by the soft min gamma. Only thing. And now there's some beautiful fact, and that's not at all straightforward. So there are actually many different ways to approximate a min function in a soft way. So the soft min is by far not the only one. But the soft min has the property that when I replace in the Bellman recursion the minimum also by the soft minimum, that this becomes a recursion of computing the soft dynamic time warping cost. This does not hold for other min approximations. For example, there's a notion of a smooth min rather than a soft min. So in the smooth min version, one typically replaces in the recursion this min by a smooth min, but then it does not hold that you also have this global property here. So one needs to be very careful. Only in the soft min case, you can replace min by soft min in the global definition and the local recursion, and you get the right thing. And the mathematical reasons are deeply rooted in convex analysis. So that also goes beyond my scope. But you have to look into convex analysis to understand this reason. Okay. So as I said, when you approach gamma, when gamma approaches 0, you get back classical dynamic time warping. And one can now easily see that the soft dynamic time warping is differentiable with regard to the C matrix. There are some questions left. Namely, when you apply it in deep learning as a loss function, you need to compute the gradient of SDTW. And you not only need to compute it, but you need to compute it efficiently. Otherwise, you cannot apply in practice. And then the last question is how actually the SDTW generalizes the alignment concept. That's a more philosophical question. And I will try to give you a feeling at least for the last question. So again, that's the definition. And what you do is you can define some sort of a pseudo probability distribution over the space of all possible alignments. So that's a huge space, exponentially large. And you define it by basically taking the inner products of a given alignment and the C matrix, take the exponential, and then normalize it in a way that P gamma Z for a fixed C becomes a probability distribution over the space of all alignments, here indexed by A. Okay, and then with regard to this probability distribution, you can compute an expected alignment, which is, so to say, the average over all possible alignment matrices weighted by these probability coefficients. So this sum is huge. And now that's a nice mathematical fact. You can show that the gradient of the soft dynamic time warping is exactly this expected alignment. And now, again, a very beautiful fact I don't show here is that you can compute the gradient again efficiently using another recursive algorithm in the complexity n times m. So this second recursion has nothing to do with the forward recursion, with the Bellman recursion. So we have two algorithms, one computing the cost and the other the gradient. Yes?
Meinard, sorry to interrupt you. Would it be possible that we can conclude in 5 minutes?
Yes, easily.
Yeah.
We are nearly done. Okay. So let's look at some examples, and that gives you the intuition, and then I stop. So let's look at the expected alignment for different gammas for a concrete cost matrix. So the expected alignment itself is a matrix. Similar to, and the alignment matrix is actually the special case of the expected alignment for gamma equals 0. So for this cost matrix, this is an optimal alignment in the classical sense. And it turns out that this is exactly the optimal, that's exactly the expected alignment for gamma equals 0. Yeah. In this case, the probability distribution is 1 for the optimal alignment and 0 everywhere else. Okay. And now when you increase the temperature, this expected alignment becomes smoothed out. So it does not assign a single cell to a single cell. It always assigns all cells, all elements in one sequence to all other elements in the other sequence in a soft way. So that's similar to an attention matrix, right? But it has more structure than an attention matrix. It still fulfills some sort of a step size and monotonicity and boundary condition. And increasing gamma, it's getting more and more blurred. In the limit case, when gamma goes to infinity, then the probability distribution becomes equally distributed. And what you get as expected alignment is simply the average over all possible alignments. And in this case, also, you can think of the expected alignment as some sort of a joint probability, the probability of any alignment going through a specific cell. And yeah, so to conclude, what I want to indicate, you can directly generalize dynamic time warping by using the soft-min. It's also possible to further generalize it using other min approximations. The nice thing with soft-min is that there is a fast forward algorithm. There's a fast gradient computation. One can show that SDDW has some downsides. It's a very poor approximation of dynamic time warping. It's a poor lower bound, but still it suffices to do gradient descent. So, and finally, it can be used as a loss function to learn from weakly aligned sequences. Also, practically, it's pretty hard to get soft dynamic time warping run. So when you have a poor initialization, you are stuck. And there are strategies to overcome this initialization problem. And also, that's a very nice thing. You can mimic many other alignment strategies using soft dynamic time warping. In particular, one can show that with specific settings of generalized SDW, you get back exactly the CTC loss. So that allows you this framing to generalize also the CTC loss. And with this, I want to conclude my presentation, where I presented 3 different ways to integrate knowledge into loss functions. And when you are interested in differentiable alignment losses with all these variants I just mentioned, I do a commercial break at the end. So there will be a tutorial at the next ISMIR conference together with Johannes, where we will detail on all these aspects within a 3 hours tutorial. Thank you.